I prepared a quite data science and also very specific to video games, so I hope you enjoy. So before we jump into it, a quick word about my team and myself. So I joined Ubisoft right after my statistics degree in the summer of 2018. The team that I joined at that time was a small data science team within a division at Ubisoft that is called Montreal User Research Lab. In general, the mandate of that service is to support all Montreal productions in everything related to player experience. So how to monitor it, how to better understand it, and most importantly, how to improve it. And as you can see, this is done in part by having players come in, try our games, play our prototypes, participate in experiments. This provides us with rich qualitative data that we can then mix with quantitative data in massive amounts coming from our in-game tracking. So as you may imagine, it's quite a multidisciplinary bunch, including all kinds of data jobs, but also backgrounds such as in biology, psychology, that kind of thing. And as player experience is a wide topic, well, we cover all kind of things related to games. So within that team, the data scientists, our roles are many. But one of them is to work hand in hand with designers and programmers to evaluate and monitor and make better specific game systems that are data driven. Because, well, as we've seen in the previous presentations, the scope of machine learning and data science is huge right now in video games. From systems that are there to assist in the creation for designers and artists, make their life easier, allow them to focus on where they can really add the most value. We had something amazing about reinforcement learning and how we can use it in many ways in our games. And then there are some specific systems within game that are inherently data driven. Some of them more commonplace like recommenders, but also others that are really unique to the specific nature of video game as a media. And one of them is the matchmaking of players in multiplayer game. And this is what I'm going to be covering tonight. So let's get started. Just to put everyone on the same page, a quick review of what it is and why we need it. So we are in 2021. Games attract a huge number of players. It's still maybe a small order of magnitude behind the most popular sports in terms of players playing it regularly, but still that's many millions of players logging in to any of the most popular game on a daily basis. And just like in any other discipline, the skill ceiling is high. There's a huge gap between someone that just started the game yesterday and actual pro players of that game in terms of skill. And so, with all of these players and this huge gap, if we only match randomly every player that come in to play the game, we are going to create some severe uh, mismatches between the players. So of course this is not fair, but it's not only not fair, it's not fun for either end of that deal. And if it's not fun, players won't stay. If they don't stay, it's not fun for us either. So really it's a win-win situation to have a good matchmaking system that will match players of similar skill together. And since nobody wants to wait, we want that matchmaking to happen quickly and minimize wait times. So this is what we essentially understand as the matchmaking problem. And it's what it's called on the outside, although on the inside, within the industry, we like to split that problem into two sub-problems. The first one, skill rating, addresses the fact that if we want to match players of similar skill together, well, we need to know their skill in the first place, or at least have a good estimate of it somehow, and as quickly as possible in these players' history. So that's the first part. The second part, matchmaking proper, is to, at any given time, look at the players that we have waiting for a match, observing their rating, and making the optimal matches in terms of skill proximity, while also keeping the waiting times under control. So these are two big topics. Today I'm going to focus only on the first one, skill rating, which is more than enough for the time that we have. So the notion of skill rating predates video games by quite a few years. The first serious system was developed for the game of chess, in fact, by a certain Mr. Elo. You might have heard of the Elo rating before. At that time, it was not really developed for matchmaking purposes, but rather just to be able to provide an overall ranking of worldwide players. Even without having them to play against each other all the time. So, and this is still a secondary use that is leveraged in online games, to display leaderboards and that kind of thing. So this is pretty much the first instance of a serious skill rating system used globally. And this system underwent many improvements throughout the year. I'm just going to outline a single one here. That's called the Glico system by a certain Mark Glickman. And the specificity of that system is that it's the first one pretty much to add a second parameter to describe the skill of the player. So the yellow system essentially had one number to describe the skill, and the higher it was, the stronger a player is supposed to be at winning the game. Now, starting with Glico, we have a second number. So in addition to the mu parameter that is kind of, the current best estimate that we have of a player's skill, we also had a sigma parameter, which, as you might imagine, describes the amount of uncertainty we have about our skill estimate for that player. So for newer players, this would be bigger, and then as that player accumulates more matches, we get more information that would go down, and this would also control the update sizes. We'll see that a bit later as well. So this worked quite well for chess. Now, 2000 is also about the time when online games started popping left and right, and in all kinds of format, not just games pitting one player against a single another. So, in fact, we could have teams of players facing each other, and even more than that, we could have 3 or 4 or even more teams all facing each other in some kind of free-for-all format. And the Glico or Elo system were not made to handle all of these relationships between players at the same time. So clearly, the video game industry needed something more. And there's something more they got in the form of the True Skill rating system. So the True Skill was developed at Microsoft. The first use case was on Halo 2, if I remember correctly. And the benefit of that system is that it could deliver good update rules for any kind of format or team or player setup. And it's a very influential system. Even today, all skill ratings in all games pretty much are at least based on their basis. Based on a true skill or some variation of it, and then there are some enhancements, that kind of thing. But it's really central to the industry, and since it's so central, I'm going to take a few minutes to describe it into more details, and take a sip of water as well. So the true skill system relies first on a model of how skills should relate to match result. And that model is very smart, it's very neat. It relies on only 4 basic assumptions. So the first assumption is that every player has a skill value. That's a real number. It may evolve slowly with time, but most importantly, it's unknown to us. Now, second assumption is that at any given game, a player will display a certain level of performance. And that performance is not constant. It's a random variable, which makes perfect sense. We are not robots. And to make it simple, we assume that this performance is in fact normally distributed, centered around that player's hidden skill value, and with some variance parameter, usually called beta. And it's a hyperparameter of the model, if you will. So it kind of represents how variable the performance can be in that specific game. So it will be influenced by how random a game is, for example. So that's second assumption for you. The third one is about team play. So when players form a team, the performance of the team in a specific match is going to be the sum of the performance of each individual player. So essentially saying that the whole is the sum of its parts, which is challengeable, sure, but we'll see some way to wiggle around that assumption later. But for right now, we'll keep it because it really helps to maintain a stability of the model, that kind of thing. And finally, last assumption is that the team displaying the highest performance in a given match is the winning team, and the team displaying the second best performance would be ranked second, and so on. So with that model, if we did know the skill value of the players, we could we could not exactly predict the outcome because there's still the random performance, but we could at least uh, write down a likelihood for each match outcome. So essentially, we have this schematic here where we can go from skill value and output a probability for each match results. Now, we do not have the skill values, but we do have the match results. So in fact, we want to reverse, flip around that model somehow to get back to the skill values. And well, it so happens that flipping around a model is pretty much the definition of statistical inference. So having a model, having the outputs, and inferring the parameters of that model from the outputs, that's it. So essentially, what TrueSkills does is to, based on their ranking model, they do inference on the skill values. And what kind of inference? Bayesian inference, more specifically, and we'll see why in just a second. In fact, I won't dwell too much into the formulas and details as it's almost 8 already. But essentially, the Bayesian paradigm in statistics is that the universe is constantly sending us new information, and we can use this information to update our current beliefs about the world, or more modestly, in our case, about the player's skills. So this is what we're going to do exactly. So after initializing all players to some baseline value of parameters, so everyone with the same starting new and sigma parameters, each match update is going to be a Bayesian update for the system. So I mean, I detailed the Bayesian ingredients here, so you can review them on YouTube. But essentially, uh, the idea is that the system at each match will take as prior information the skills of the player, will observe the match outcome, and according to the rules of the Bayes statistics, will output the updated, more up to date and more accurate ratings for the player after that match. And so essentially, it's just taking the quantities and the model as we described, writing it down in math, and putting it together. There are some details about the hyperparameters. So, for example, I mentioned the beta parameter earlier that controls the team performance. There's also another hyperparameter controlling the probability of having a draw, a tie, and then another one controlling how quickly the skill of the players can vary from one match to another. And essentially, what we do with these hyperparameters is that we 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 uh, we train them, grid search or over a long history of matches to make it quite robust. That's it. And then there's another detail that, in fact, this formula, we cannot like write it down exactly, because if we did so, at every update, the rule will become more and more complex because of the past matches. So we do kind of an approximation to make it so the rule has the same shape every time. And this is, in fact, the main contribution from the TrueSkills system, is to provide such an update, such an approximation that works for any kind of team and player setup. And there are other alternatives to TrueSkill as well, but the essential working is the same, the model as well. But what is really interesting is that no matter the exact algorithm used, they all agree on the update formula for when there are only two teams facing each other. And not only they agree, but this formula is in fact writable in closed form. So we can actually write down the formula and understand it, not in 3 seconds, because it's still quite a good chunk of math, even in the particular case that I describe here. But if you take the time to look at that formula, you can make some observation about some constant behaviors that you might expect about this one. For example, the fact that you have that sigma squared for one of the player in the top formula, it means that the bigger the uncertainty on the player's skill, the bigger their update is going to be in the beginning, which makes perfect sense. So I listed a few of these evidences that we can infer from just looking carefully at the formula. And I find it quite neat that in this era of concern and issues around the algorithmic transparency, that this rather old solution is in fact perfectly understandable and quite intuitive in the way it provides player updates. So I think that's quite neat. But yeah, so that's and also that's the most technical I'm going to go today. So don't worry, and let's just keep in mind that TrueSkill takes prior player ratings, takes a match results, and outputs better player rating after the match. And so it works quite well. But now the big question 15 years later is, how do we enhance it? How do we make it better? And that's what I'm going to cover in the last minutes of that talk. Let me grab another sip. So the idea here is that right now the true skill model, it only uses the actual match result and the prior skills of the player. But in fact, there's much more information in game, especially these days. We have so much data that we can leverage, and it would be nice to use it. And in fact, it's very interesting to use it because, as you probably know, there are much more than the player's skill that can explain the actual result of a match. For example, a game nowadays exhibit a huge variety of options in terms of game mode, for example, where we can play the game by different sets of rules, and then you have many different characters, for example, or classes that a player can choose from, and a player might not be as equally proficient with each of these classes or in each of these game modes. And so if the system does not see that, it will be less precise. Same thing is true for maps. For example, some maps or arenas might provide a particular advantage or disadvantage to the attacking team, say. And again, if we do not take account of that, just average it out in the system, well, we are missing so opportunity to have a more precise probability of match outcome, and so less precise updates on the player skills as well. And there are other aspects. So I mentioned before the fact that players that play well in squad in fact might be better than just the sum of their individual parts, and this is what we observe often in PvP games. So when friends voluntarily squad together to form a team, they are going to perform usually better than individual players just being randomly matched on the internet. All other things being equal, so supposing that everyone has the same skill, the team of friends is advantaged just because they are going to cooperate better. And so these are all factors that we might want to take into account and to incorporate into a true skill or any algorithm we have somehow. And how would we do that? First of all, well, we need to know which factors we want to incorporate, which one are meaningful to add to the system. And one way to look at this is to build what we call a calibration graph. So the idea is that we take a big history of matches, of player matches, in fact, and for each player match, we bin them according to some secondary factor that we are interested in assessing. And this is what we plot on the x-axis. So in that fictive example, it would be the personal points of score acquired in the previous match. And then what we do with all of these player matches is that we display an average line describing first what was the expected win rate for that subgroup according to the system, so only according to the skill ratings without using that factor. And then we display the second line, which is the actual observed win rates for all player matches in that group. And if these two do not coincide sufficiently, well, it's a good reason to think that this factor is in fact not being well taken into account right now just by the info that we have, and we should add it to the model. And this would be the case here with this made up data. Then not only do we need to consider individual factors, in fact, interaction between factors is also very important. So I mentioned earlier that playing in teams, where forming voluntarily a squad or a party is linked with better match results at equal skill. But in fact, it might only be the case if you are skilled beyond some minimal level of proficiency. So for example, here the advantage of playing in teams would really start to show up for players that are skilled at 20 or higher. So in that case, it would be interesting to not only take squad size as a factor, but squad size coupled with average skill range of the team, so that we can make that difference. So this is how we detect factors to add to the model. Now, there's still the question of how exactly do we change the model to accommodate this. So once again, the true skill crew is here to the rescue with what they call a true skill 2. So true skill 2, it's in fact a bunch of possible enhancements to the base true skill model. And the idea here is simply that, I mentioned earlier how the player skill is in fact a duo of parameter with the center parameter and the uncertainty parameter. Well, the idea, if you have additional factors, is to incorporate them in the skill of each player, so that each player is now described not only by two numbers but also by a bunch of offset for each category of your explaining factors, and then some additional variance parameters. So the first thing that we realize with this is that, well, it's quite a heavy way to represent these additional factors. So to finish today, I'd like to introduce you to some other more lightweighted approach to incorporate additional factor. And this is what we internally call phantom players, because it sounds cool. So the idea with phantom players, so suppose, for example, that map is an important factor to explain match results in your game. So what you do is that for each category or sub-level of your factor, so in our cases, for each map, we create a player, a phantom player. So it's initialized like any other player with its skill parameters. The only difference is that it's not an actual player, it's just a fictive construct. And then in any match where a specific map is called for, we simply add the phantom player to one of the teams. So by default, let's say we always add the map phantom player to the attacking team, and the skill of that player might be positive, it might be negative, depending if the map is positive or negative in terms of advantage to the attacking team. And the idea is that the skill of the map is learned in the same way that we learn about the skill of the other players. So in fact, we do not have to change our model at all. We only have to add players, have a small route to add the appropriate fictive player to the mix. And so, for example, this is better because suppose that we have two teams of perfectly equal skill, but they play on a map that is providing a small advantage to the attacking team, say. Well, if we take it into account for the phantom player, now the system, instead of predicting an equal outcome, will be expecting a win from team one, so that if team one does win, well, they are going to get a positive skill update, but that update is going to be more conservative, smaller compared to what it should be had there been a tie expected. So this is how these phantom players can improve the updates and the global convergence of the system. So it's a really neat addition to your skill. It doesn't require any any additional model assumptions or model constructions. It's just having a few more players in your million players base. So it's really lightweight. And what's really important, the third point, is that once these players have converged to their pretty much to their actual skill, and they're going to converge fast because they play so many matches. Every time a specific map or a specific instance of a factor is called for, their skill rating then is a kind of a representation of how imbalanced that specific factor is. So, for example, you could target the phantom players representing the maps with the highest or the lowest skill rating, and this would be good targets for a balancing pass eventually. For example, just another example, if you had a phantom players representing player experience, say in terms of match, well, once these skills are well learned, you could display a kind of learning curve for your game and see where it's most steep and whether you want to do something about that. So again, this is a quite neat way to leverage data into your basic skill rating system, and it's also another win for explainable AI. Just as a last closing word, these are contributors, past and present, to the data science team that worked to some extent on that topic with me. So I leave them here on display for a few seconds for you to see.
Do you have any kind of micro prediction systems to predict if a player will join the match soon, like in 10 seconds, this player could potentially be better matched than those who are already waiting?
That's a great question. So this is a bit more about the other part of the matchmaking question, but I'm super happy to talk about it too. So the idea is that this is already being put in place in some parts of the industry. I cannot be very vocal about what's going on internally in my company. I'm sure you'll understand that. But if you can look, for example, on YouTube about a talk about something called True Match, I'll let you guess which team is behind that. But the idea is exactly that, to try to build a model of how it's likely for players in specific skill buckets, say, to join the waiting line in the next seconds, in the next minute, to see see, to inform your system about whether it's time to match that player more liberally, or wait a bit more for that player to get a better match if you wait a few more seconds. So yeah, this is mostly done right now by leveraging, have the fact that from one day to another, matchmaking numbers and player densities are quite stable or similar from one day to another. So then you can start to expect if such a player is going to join the queue or not, and if not, you can start expanding your range of tolerance for matching that player in terms of skill distance.
Do you consider ethics and bias in the matchmaking process? Are you able to identify cheaters, F2P, or players that are putting big money into the game? How to ensure a fair matchmaking process if the interest of the company could be to favor players that spend lots of money on the game?
This is a very good question. So I think I'm authorized to say that we do not leverage. We do know which players spend in the game and which do not, but this is not something that we leverage in matchmaking. I do know that in some parts of the industries these things are being done. For example, it won't necessarily be well. Yeah, it might be a consider a favor. So, for example, I've heard rumors. I don't know what game it is about, but that if a player buys something, some cosmetic item, that player will be matched with players of lower skill. So there's going to be like a kind of negative bias into the 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 players they're matched against, so that they get a few wins after their purchase and feel good about it. I've heard about these strategies, but I don't know of any specific game implementing them, and I don't know of any in Ubisoft that does this. Now, about the cheater part, so cheater and identification is a huge topic. So it's all games have many kinds of systems like that. Some of them have juries, so I mean it's a whole other topic to identify cheaters. But usually, if we can identify cheaters, we do not match them at all. We just do not let them play. We suspend or ban the account. But I do know of other places in the industry where they if they feel confident enough about the cheater they identify, they match them in a specific queue with all of the other cheaters. I'm not sure. I'm not sure what that looks like, but it must be quite interesting. But I must say, cheater detection is a very difficult topic in video game. There are good advances, but it's also a bit of a cat and mouse problem.
I think cheating does certainly happen. How aware the studio is and what they do is completely
It's
completely
yeah,
different thing.
it's always it's always a problem of there's always the transparency trade-off with that kind of thing. I mean because the more we see, the more we give tools for cheater to go around what we're doing. So there's that element as well. But what's interesting is that the problem is addressed in many ways in the industry right now. So one way is focused on detecting better what's going on, and the other part is also making it harder software wise and server wise and that kind of thing for cheats to take place in the first place. So it's interesting to that there are many ways to confront this, but it's a big problem. It's also a big point to ponder, for example, between for a game, for example, to go free to play or to go paying. The thing is that when a game is free to play, it's not damaging to have your account banned or suspended or that kind of thing. So if you want to go the free to play road, you have to be super confident in your capacity to handle not only cheaters but also smurfs and that kind of thing. So it's a big transversal issue in the industry right now, no doubt.
What's a Smurf?
So a Smurf is a player usually quite good at a game that will voluntarily create a new account to be able to play against players that are not of their
I
skills. So
see.
usually weaker players, and so there are many ways to do this. So the quickest way is to start a new account if you can afford it or if it's free, and otherwise it's the idea is that you can kind of I mean, I've described what the skill rating system is, but in that essence you can still game the system by voluntarily losing repeatedly until you end up in a lower skill bracket, say. There are many kinds of mechanisms that we can add against that, but so that's Smurfing in a nutshell.